Okay, I think what confuses a lot of people about this problem is they don't know what the Kn for. The Kn is for the neutralization of alanine over vitamin C. The Kn means that you've reacted equal amounts of alanine with equal amounts of your weak base. I'm sorry, I can't talk today. This problem asks for the equilibrium constant for the neutralization of alanine with vitamin C. What you're doing is you're reacting a weak acid with a weak base. Now, I can cut to the chase and give you the formula and tell you that when you react a weak acid with a weak base, the equilibrium constant is going to be equal to the Ka times the Kb divided by the Kw. But how did we get there? And I could have sworn I remember doing this in lecture, but I may not have. I often invent and dream really awesome lectures, so that's not unlike me. So let's go through the proof. Y is the equilibrium constant for the neutralization of a weak acid with a weak base equal to Ka times Kw times Kb. Well, to answer that question, the first thing we've got to do is we've got to write a neutralization reaction. To do that, I'm going to use a generic acid, HA, and I'm going to react it with a generic base, B negative. And at the equivalency point, they're going to react, and they're going to form their conjugate acids and bases. That is the reaction to which Kn is the equilibrium constant. The question is, how can we find this value easily? We can do it by using our Hess's law property, or our addition of little reactions. I know that what I really have going on here is a series of two smaller reactions. I know that I have my acid wanting to behave like an acid. And when it does that, it has an equilibrium constant of Ka. I also know that my weak base wants to behave like a weak base. If I add these two reactions together, then I get HA plus B negative plus 2 waters yields A negative plus HB plus hydronium plus hydroxide. Whenever you add two reactions, what do you do to their equilibrium constant? You multiply their equilibrium constant. So I have Ka times Kb as the equilibrium constant for the reaction that I just wrote here. If you look at this reaction, it matches my neutralization reaction, except for this annoying water. I've got some annoying water. How can I get rid of it? By using my Kw reaction. But I'm going to flip it. Remember, Kw is the equilibrium constant for the reaction. 2 moles of water yields 1 mole of hydronium plus 1 mole of hydroxide. So what I'm going to do is I'm going to flip it. And I'm going to have hydronium plus hydroxide yielding 2 moles of water. If I reverse reaction, what do I do to their equilibrium constant? I take the multiplicative inverse of it, or 1 over Kw. So, if I add the reverse of my Kw reaction, come on, if I add the reverse of my Kw reaction, if I take that and I add it to the sum of my Ka and my Kb reactions, look what happens. Oh, 2 waters there gone. Whoops, what did I do over here? I'm again enjoying myself talking so much. That should have been 2 waters over there. I hope that didn't mess anybody up. That allows me to cross out my 2 waters. Crossing them out there and crossing them out there. Allows me to cross out my hydronium. Allows me to cross out my hydroxide. So that gives me HA plus B negative yields A negative plus HB over Ka times Kw divided by, Ka times Kb divided by Kw is equal to the equilibrium constant for my neutralization reaction. And that's where it comes from. Ta-da! So there's your proof. So if we go back to our specific problem, which is what you were really asking about anyway, we have a Ka of 8.0 times 10 to the negative 5th. We have a Kb of 4.3 times 10 to the negative 10th. And you've memorized Kw is 10 to the negative 14th. That's going to give you that gives me 3 point, that can't be right. Can it? That gives me apparently 3.44. Just a second here. Let me check and make sure I did everything in my calculator correctly. Yeah, I did everything in my calculator correctly. So that gives me 3.4. Very specifically, it gives me 3.44. But you only have 2 sig figs to deal with. So it's really 3.4 is the better answer since you only have 2 sig figs. So that's your equilibrium constant for your neutralization reaction. Now, they ask how much alanine remains at equilibrium. What's your alanine? Well, your alanine is your base, so it's going to be the bottom part of your fraction. What I hate is they ask, does much. We have something, remember when we were talking about equilibrium constants, and we went to the thousands? We said greater than that, we had more product. Greater than that, we had more reactants. In this range here, we said basically products were kind of equal to reactants. We're really close to 1 here, which means that we're definitely between our thousands. So we have significant amounts of everything present. So I would answer that yes, although I really hate relative phrases such as much. But that's how you do that one.